Knock on the wall of a typical American house, and it may sound almost empty. Open that wall during construction, and the illusion becomes stronger. Thin wooden studs stand in rows. Sheet material covers one side. Drywall will cover the other. Between them are insulation, wiring, pipes, and sometimes ductwork. To anyone accustomed to brick, stone, or concrete, this can look less like permanent shelter than a carefully finished wooden box. Yet that box may carry 2 or 3 floors. It may stand for a century. In an earthquake, its lightness and flexibility can help it survive forces that damage heavier, more brittle structures. But one bad connection can let wind tear at the roof. One missing piece of flashing can allow water to rot the wall invisibly. One unprotected opening can become a pathway for fire. So is the American house actually flimsy? Or is its strength located somewhere most people never think to look? The answer begins with a national problem. How do you build millions of houses across a continent when people, cities, technology, and expectations are changing faster than traditional construction can keep up? Before light frame construction, a substantial wooden building often depended on heavy timber. Large posts and beams carried the structure. Skilled carpenters cut mortises, tenons, braces, and joints so the pieces locked together. The frame could be exceptionally durable, but it required large timbers, difficult handling, and workers who knew how to shape every important connection. Masonry offered another kind of permanence. Brick and stone could produce thick, durable walls, but those walls were heavy, labor-intensive, and difficult to alter once completed. Both systems made sense where skilled trades and material supplies had developed over generations. The United States was developing under different pressure. New towns appeared quickly. Existing cities expanded. Families moved into places where the local building industry was often as new as the community itself. Few places revealed that pressure more clearly than 19th century Chicago. Chicago needed buildings at extraordinary speed. Houses, shops, warehouses, churches, and workshops had to rise while the city was still creating the labor force and supply networks required to build them. The region had lumber. Sawmills could turn logs into smaller, increasingly standardized pieces. Manufactured nails were becoming more available. Waterways and railroads could move materials into a rapidly growing market. But the crucial change was not simply that Americans had wood. It was that builders began treating small pieces of wood as parts of a coordinated structural system. This method became known as balloon framing. For generations, popular histories credited a Chicago carpenter with inventing it almost at once during the 1830s. The evidence tells a more complicated story. Builders had simplified timber frames long before Chicago existed. Carpenters in different places experimented with smaller members, easier joints, manufactured nails, and faster methods. In Chicago, those ideas evolved inside an unusually intense construction market. Balloon framing was less a single invention than a convergence. Standard lumber, cheap nails, mechanized milling, expanding transport, and constant pressure to build. That is the first hidden lesson inside the American wall. The system did not begin with one genius drawing a revolutionary house. It emerged because an economy was becoming capable of producing interchangeable building parts. A balloon frame replaced much of the massive timber skeleton with many thin vertical studs. Those studs could extend across more than one story. Floor members attached to the frame. Boards and braces helped resist sideways movement. Nails held connections that once required carved joinery. Each piece looked weaker than a heavy beam. Together, the pieces created a structure. A balloon frame house built in 1855 for a farmer named John C. Cowing later became important enough to be reconstructed for display by the Smithsonian. Its significance was not luxury or famous ownership. It was ordinary construction. Thin, pre-cut lumber joined with iron nails had become a credible way to make a permanent American home. That changed the relationship between skill and speed. Experienced carpenters still mattered. But every major joint no longer had to be cut as if the house were a piece of furniture. A crew could assemble a building from repeatable dimensions and familiar fasteners. Work could be divided into simpler operations. In early Chicago, lighthouses were sometimes moved through the streets rather than demolished. Their mobility was not the purpose of balloon framing, but it revealed something extraordinary. A house could be strong enough to serve as a building and light enough to be treated almost like an object. The apparent weakness was the breakthrough. But the system carried a dangerous defect. The long cavities inside balloon-framed walls could create concealed vertical pathways. Once fire entered the wall, heat and flame could travel upward toward higher floors and the roof before occupants understood what was happening. Wooden cities faced many other fire dangers: combustible roofs, closely packed buildings, heating equipment, industrial activity, and limited firefighting capacity. Balloon framing did not create urban fire by itself, but its continuous cavities could make an existing fire harder to contain. The system that accelerated American growth now had to be redesigned around one of its own consequences. The answer was not to abandon light framing. It was to reorganize it. Platform framing gradually became the dominant method. Instead of using long studs across several levels, builders constructed one floor at a time. First came a floor platform. Walls were assembled and raised on it. The next floor created another platform above them, then another set of walls, then the roof. This reduced dependence on unusually long lumber. It gave crews a flat working surface at each level. It made the sequence easier to repeat, and floor assemblies interrupted the continuous wall cavities that made balloon frames vulnerable to hidden fire spread. Fire was one reason for the change, but not the only one. Shorter lumber was easier to obtain and handle. Floor-by-floor construction fit standardized materials and predictable work stages. Platform framing turned a light structural idea into a scalable production method. Then something even more consequential happened. The frame became a grid around which the rest of the building industry could organize. Regular stud spacing allowed insulation to be manufactured in standard widths. Windows and doors could be produced for common openings. Gypsum board could arrive in large sheets. Electrical boxes, pipes, cabinets, connectors, and fasteners could be designed around familiar dimensions. Later, plywood and oriented strand board allowed workers to cover large areas quickly while contributing resistance against sideways forces. Factory-built roof trusses moved difficult roof geometry away from the building site. Engineered joists could span floors with predictable dimensions. More of the house became a collection of products designed to fit other products. This was not simply cheaper construction, it was compatibility. And compatibility is what turns a technique into a system. By the early 20th century, wood construction was also becoming an object of organized engineering research. The United States Forest Products Laboratory began operating in 1910. Its researchers studied wood properties, fasteners, moisture, fire, engineered products, finishes, and structural performance. The Federal Wood Handbook, first issued in 1935 and repeatedly revised, helped convert practical knowledge into published engineering information. That history separates two ideas often confused. Light frame construction is not the absence of engineering. It is an engineered method that can be executed well or badly. The housing demand after the Second World War pushed the system to another level. Builders increasingly organized residential construction as a sequence of specialized operations. One crew prepared the foundation. Another framed floors and walls. Others installed roofing, plumbing, wiring, heating, insulation, drywall, cabinets, and finishes. Standard plans reduced variation. Repeated details reduced uncertainty. Manufacturers supplied components for each stage. A house remained fixed to one piece of land, but its production began to resemble an assembly line spread across a construction site. This is why the hollow wall became one of the most valuable spaces in the American home. It was not simply empty. It became infrastructure. Wires, pipes, insulation, and mechanical services could pass through it. Future owners could open the wall, repair a line, add an outlet, change a room, or install technology that did not exist when the house was built. Electric lighting, indoor plumbing, central heating, air conditioning, telephone cable. Internet. The American wall could absorb new machinery because it had never been one solid object. But that flexibility created another misunderstanding. A structural system, a finished material, and workmanship are not the same thing. A wood frame may safely carry its required loads. The roof covering may still be designed for periodic replacement. The siding may have a different service life from the frame. And a valid design can fail prematurely if a critical detail is installed incorrectly. Calling all of that flimsy hides the real question. Which part failed? The structure? The protective enclosure? A replaceable component? Or the workmanship connecting them? Modern building codes attempt to define minimum acceptable performance. They address structural loads, fire protection, moisture control, energy performance, and regional hazards such as wind, snow, earthquakes, or flooding. They also require measures that interrupt concealed fire pathways. But American building regulation is not one uniform national command. Model codes are adopted and modified by states and local jurisdictions. Climate, enforcement, amendments, and inspection capacity vary. A house in coastal Florida faces different pressures from one in Minnesota. A California house cannot be detailed exactly like one in a low seismic region. There is no single American house. There is a shared construction language adapted through local rules, climates, companies, and crews. And code compliance does not mean every component has been made as durable or expensive as possible. A code generally establishes an acceptable threshold for safety and performance. It does not require every roof, window, floor, appliance, or exterior finish to last for generations. That is where the American trade-off becomes visible. The structure may endure while layers attached to it are replaced. Roofing wears, sealants fail, paint fades. Mechanical equipment reaches the end of its service life. The house survives partly because it can be renewed in pieces. The American house often places permanence in the frame and adaptability around it. But the strategy depends on controlling water. Wood can perform for a very long time when protected and dry. Persistent moisture changes the calculation. Water entering around a window, roof intersection, wall penetration, or foundation can remain hidden. It can damage insulation, finishes, fasteners, and framing before a stain appears inside. That is why a thin piece of flashing can matter more than a thick piece of lumber. The siding is not expected to stop every drop by itself. The wall needs a continuous drainage layer behind it. Openings must be integrated so water flows outward rather than into the cavity. The wall succeeds through layers: structure, sheathing, water control, air control, insulation, interior finish. Remove one critical function, and the entire assembly can appear defective. This is the third hidden lesson inside the American house. Its strength is distributed. It does not live in one material. Disasters make that distribution impossible to ignore. During an earthquake, a lighter structure generally carries less mass, and properly connected wood framing can deform without behaving like heavy, brittle construction. But flexibility is not magic. Weak connections between foundation, walls, floors, and roof can still produce failure. During a hurricane, the crucial question may be whether forces can travel through a continuous chain of connections from the roof to the foundation. A strong roof covering cannot save a house if the roof separates from the walls. In wildfire country, the danger is not limited to the main wall material. Wind-driven embers can enter vents, collect at vulnerable edges, ignite nearby combustibles, or penetrate gaps in roof assemblies that appear fire-resistant. Different hazards attack different links. The lesson is not that wood always performs better. It is not that masonry always performs better. It is that buildings survive as assemblies. Mass, flexibility, connections, fire resistance, drainage, foundations, openings, roofs, and maintenance interact. An expensive material can perform badly inside a careless system. A modest material can perform remarkably well inside a disciplined one. This helps explain why America did not abandon wood framing as it became wealthier. By then, light frame construction was no longer merely a material choice. It was an ecosystem. Builders knew how to estimate it. Suppliers stocked products for it. Factories made panels, trusses, joists, windows, insulation, and connectors around it. Codes contained established methods for approving it. Trades knew how to install services within it. Homeowners knew how to repair and remodel it. Changing the wall would mean changing far more than the wall. It could mean changing the foundation, labor force, schedule, supply chain, mechanical design, inspection process, repair methods, and price. That accumulated dependency is why a building system can persist even when alternatives offer real advantages. Masonry can provide mass, long-lasting surfaces, and fire resistance. Concrete can offer strength and durability under appropriate design. Light framing offers speed, flexibility, low weight, accessible service cavities, and compatibility with standardized products. Every system has failure modes. America did not choose between quality and no quality. It chose which problems its dominant system would solve most efficiently and which would be managed through codes, detailing, maintenance, insurance, and replacement. That choice also shaped the form of American homes. Construction efficiency can make additional rooms and features less expensive, but savings do not automatically become lower prices. They can become more floor area, larger kitchens, additional bathrooms, attached garages, complex roof lines, and more equipment. The efficiency of the frame helped Americans build more house, not merely cheaper house. That is why changing the framing material alone would not solve housing affordability. Land, zoning, permits, labor, financing, infrastructure, location, size, and consumer expectations also determine cost. The building system creates possibilities. The market and public rules determine how those possibilities are used. Return now to the wall that sounded hollow. Its studs are not working alone. Sheathing helps resist sideways movement. Fasteners transfer forces. Floors and roofs distribute loads. Fire blocking interrupts concealed pathways. Flashing and drainage layers manage water. Insulation and air control manage heat and moisture. Drywall contributes fire protection and interior enclosure. Every part depends on another part doing its job. When those connections are designed, installed, inspected, and maintained properly, the wall is not an unfinished version of masonry. It is a different technology. When the chain is broken, the failure can remain hidden until repair becomes expensive. That is the genuine weakness of the American house. Not simply that its pieces are light, that a system built for speed and efficiency can magnify the consequences of careless execution. Chicago helped reveal the opportunity. A growing city needed a way to transform manufactured lumber and nails into buildings faster than traditional heavy construction allowed. Balloon framing showed that strength could emerge from many small pieces. Its fire problems exposed the cost of continuous cavities. Platform framing reorganized the structure floor by floor. Industrial products made the grid compatible and repeatable. Research and codes converted experience into engineering rules. Postwar builders turned those rules into a national production system. America, before this transformation, built through regional materials, heavy structures, and craft traditions difficult to reproduce rapidly across a continent. America after it possessed a common housing language: standardized lumber, nailed connections, hollow service cavities, sheet materials, replaceable layers, specialized crews, and buildings designed to accept future change. That system did not make every American house good. It made American houses scalable. And that distinction is the answer. The American house does not survive because every piece is massive. It survives because thousands of ordinary pieces are supposed to work together. Its greatest achievement is that the system can be repeated. Its greatest risk is that repetition can hide mistakes. The wall sounds hollow because much of its strength is invisible. It is in the geometry, the connections, the layers, the standards, the labor, and nearly 2 centuries of American industry organized behind them. American houses are not built this way because permanence was abandoned. They are built this way because America created a form of permanence based on systems, repair, replacement, and change. A house designed not to remain untouched forever, but to keep functioning as the country around it changes.